Hello, it's Jin Liu from the University of New South Wales in Australia. Here, I would like to share with you our work, Nephalai, towards LPWAN CRAN with physical layer compression. In this work, we propose a compressive sensing-based cloud radio access network to reduce the uplink bitrate of the physical layer between the gateways and the cloud server for multi-channel LPWAN. We have two versions of presentations. One is 5 minutes as a briefing, and the other is 20 minutes with more details. This is a longer version of our presentation, and we will introduce the system and techniques in detail. Here is the structure of the presentation. We will first give you an overview of the LPWAN CRAN system, and then discuss the motivation. Compression will then be discussed in detail, followed by a campus-wide evaluation and a conclusion based on the evaluation. What is Nephalai? What is LPWAN CRAN? In this research, we mainly focus on LoRaWAN as a representative of LPWAN technologies. First of all, let's have a look at the system. Here is an overview of the traditional LoRaWAN network. End devices send out signals with chirp spreading spectrum modulation, or CSS modulation. Gateways demodulate and decode the signal to obtain the packets. The packets are then forwarded via internet or intranet to the cloud. The network server or end application server in the cloud will process the packets. An acknowledgement packet will then send back to the end devices to have a closed loop. Now for CRAN, we move the demodulation and decoding to the cloud. Instead of detection, demodulation and decoding with specific hardware, the gateways only need to compress the signal with any suitable radio receiver and general purpose processors, such as a PC or embedded system. The compressed physical layer are then forwarded to a cloud via any available network. It could be wired or wireless. It could be even with satellites, such as the Starlinks from a remote area. In the cloud, the server will first reconstruct the physical layer and then do the work that are used to be handled by edge devices or edge gateways, such as detection, demodulation, decoding, and processing. In general, for the gateways, a specific hardware is not necessary. Any radio head with a host can contribute to this network. Note that to follow the practice of CRAN, we have changed the intranet network from a backhaul to a fronthaul. It is clear that with this CRAN, the bandwidth of the fronthaul is more or less increased. Now let's crack open one gateway. One possible implementation is with software-defined radio, or SDR. Inside the gateway, multi-channel signal is received by the antenna. An SDR sampling a wideband, and then each subchannel is extracted with frequency conversion, low-pass filtering, and decimation to its Nyquist sampling rate. If a channel is detected, active, the physical layer will be compressed and uploaded to the cloud for further processing. As a trick here, the digital signal processing and compression can be combined as one matrix for better efficiency. Our implementation shows that a low-power embedded system can handle the processing and compression for quite a number of multiple channels. Till now, we have gained an overview of the Nephalai system. One may ask, what's the motivation behind it? To upgrade the traditional LoRaWAN network architecture to a CRAN, or explicitly, why use CRAN and why compression? For the first question, CRAN can provide network capacity for more than 8 channels, while the commercial gateways can currently only support 8 channels. It also provides the flexibility to involve the community to help quickly deploy the infrastructure, because any low-cost radio head instead of a specific hardware can be used for the CRAN. For example, even a $10 TV antenna or RTL SDR can be used. Besides, CRAN can provide extra benefit such as spatial diversity for signal strength improvement. The second question, why compression? Because such a CRAN can generate a huge bandwidth for the offloading network. You may use the optic fiber, but the cost for the data rate may not be acceptable, especially for low-cost IoT applications. And such bandwidth is beyond most home internet, which may limit our vision for community involvement. Of course, the community will not be happy if the CRAN consumes too much bandwidth of our network. They will not do the favor for us. Okay, now, we all know compressed LPWAN CRAN is beneficial. Then comes the question, how can we compress it? Next is the technical part, and we will discuss compression in detail. We choose to use compressive sensing, which is simple and efficient. First of all, here we briefly review compressive sensing. I cite Banani's lecture notes here, which I personally really appreciate. It clearly shows that how compressive sensing is being done. It also shows the key factors, including the projection or measurement matrix phi, the dictionary psi, and the sparse vector S and the raw data X, as well as the compressed signal Y. Of course, one basic condition for compressive sensing is RPI condition. For brevity, we here skip the discussion of RIP, and we assume the condition is always met. In our case, we first get X, a complex value sequence indicating the I and Q of the received signal for one subchannel, which is processed with the frequency conversion low-pass filter and decimated to its Nyquist sampling rate. Then we do compression by multiply X with the measurement matrix phi, and then we get a compressed vector Y. The measurement matrix phi is a symmetric Bernoulli matrix with random positive and negative 1. That is plus and minus 1. The length of Y is much less than that of X. The ratio of the reduced samples over the original samples is defined as a compression ratio, which means the larger the compression ratio, the smaller the Y here. After that, Y is transmitted via any suitable network to the cloud. In the cloud, our reconstruction is done with L1 minimization. Besides, in some cases, the reconstruction of physical layer is not necessary. Instead, we can directly solve the to solve the modulated information with a residual minimization, and with multiple copies of the signal that is sent by the same transmitter but received by multiple gateways. We propose a joint decoding, which can further increase overall performance by exploiting the spatial diversity. We find that an algorithm similar to maximum ratio combining, or MRC, can achieve the best performance. Overall, the key to a successful compressive sensing is to find the sparsity. Is the signal sparse? If we look deep into the signal, we'll find that the signal is actually very sparse. Here in figure A to figure D, here you see that the signal between two white dashed lines indicate one symbol. For demodulation procedure, we first multiply the raw symbol in figure A with a downchirp and get a flat signal in time frequency domain as shown in figure C. And then apply a DFT or FFT on the flat signal. You'll see the result in frequency domain is very sparse as shown in figure E. Since the frequency domain is very sparse, you can inverse the whole procedure and obtain the dictionary by an inversed downchirp matrix and an inversed DFT matrix. Even the signal is not detected or aligned in advance as shown in figure B, the signal is still very sparse as shown down there in figure F. Follow the procedure we proposed here, we can get a general sparse dictionary without symbol alignment in advance, which means that the detection is not required by the gateway. As the heavy duty of detection and calibration can then be moved up to the cloud. So for the gateway, it's only minimal computation for basic DSP and decompression. And based on the results of frequency domain of the well-aligned and not well-aligned symbols as shown in the previous slide, the well-aligned symbol is more sparse, as we see in figure C in previous slide, which may achieve higher compression ratio than that is not well-aligned. However, the alignment is not guaranteed by LoRaWAN protocol. If without detection, the symbol are mostly not aligned. The chance is that if a synchronized transmission mechanism is maintained by both transmitter and receiver, the symbol can be regarded as aligned. We found that the beacon in LoRaWAN class B and slotted Aloha mechanism can provide a similar synchronization, which may have benefited the compression ratio. Again, this is not guaranteed, but we would like to point out that here, if in the future the network structure involve such synchronized transmission scheme, it will definitely beneficial. Here we just briefly show that how sparse our dictionary is. By comparing traditional DFT or DCT dictionary, the symbol either aligned or not aligned on our dictionary is both orders of magnitude less sparse than those with DFT and or DCT dictionaries. We also provide the algorithm for directly solving with residual minimization. The algorithm first determines the sparsity, that is, how many significant words out of the dictionary is included in a compressed vector. Then we solve the LPWAN minimization and enumerate each possible combination of the sparsity and keep the least residual as the final solutions. We found that residual minimization has better performance against noise than that is solved with magnitude. Finally, as for joint decoding, we propose an algorithm similar to maximum ratio combining to combine a signal weighted by the ASINR. In theory, it has equivalent performance as those uncompressed signal with co-phasing combining. But here we leverage LPWAN minimization and residual minimization to facilitate the joint decoding. It can be done without explicitly reconstructing the signal. Note that in the cloud, if a signal is not detected and calibrated for a CFO, reconstruction is still needed. But when the preamble is processed, the relevant parameters estimated, the payload can then be handled without reconstruction, but directly decode or joint decoding. So it comes the question, how's it work? What's the performance? First, we implemented the prototype with software-defined radio, or SDR, and embedded systems. We evaluate the performance in our campus. We have 4 prototypes gateways deployed in different places indoor. We use a LoRa transmitter to mimic different application scenarios, such as water pump on the low, occupancy detectors in the basement, and so on. So they will have different SNR and a signal distortion. Here is the result for the evaluation. With a single gateway, we found that the compression ratio is affected by the spreading factor of LoRaWAN and signal to noise ratio SNR, which means that you can define a suitable compression ratio based on those 2 factors to maintain the packet reception rate without the system downgrading. With 4 gateways, we prove that even compressed signal can still improve the overall performance with multiple gateways compared to a system with only 1 gateway, or simply the system benefits from spatial diversity as well. Last but not least, we draw a conclusion based on our campus-wide evaluation. Number 1, up to 93.7% physical layers can be reduced without degradation in the packet reception rate when we evaluate at spreading factor 9 and signal to noise ratio 6 dB. Number 2, with 4 gateways, the system achieves 1.7 times packet reception rate with 87.5% compression, which is equivalent to a 70% longer battery life. Thanks for watching. That's the end of the presentation. If you have any questions, please send me emails. Hope our work can help the community towards building up hybrid LPWAN community network. Hope you enjoyed. Thank you very much.